screen. All right. The screen share looks a little bit different now. I will explain in a moment. But first of all, my name is Radovan Bast, University of Tromsø, and I will discuss with you how to choose memory settings for your job and number of cores. And so that you can find where we are and the material that I will follow. So on top of the HackMD, there is the schedule, and here are links to the material. And if you like, you can open it up. I will follow this material, but I will not show the slides. We will now really take a step back and go more hands-on. I will be in the terminal, and I want to really try some of these things out that Ole mentioned earlier. So I hope I will make it really practical. My plan is then for the next 40 minutes to demonstrate some of these techniques and why it matters. And then we will take another break. And hopefully we will have time for an exercise. So after the break then, my plan is to do a 20-minute exercise where you can try some of these techniques that I will demonstrate. You can try them out. Now, some more practical things. The screen share that I'm using is now a little bit different. It's like portrait, it's not landscape. And my aim with this is that you can put my screen share on half of your screen, either on the left half or right half. And on the other half of your screen, like a good way to participate is to have the HackMD open so that you can ask questions. In the HackMD, if you haven't written anything in the HackMD, I recommend everybody to at least switch to edit and then switch back to view, because you need to be at least once in edit mode so that the HackMD keeps updating. And here, so on the other half of your screen, I encourage everybody to ask me lots of questions. And later, when we go into an exercise, you can use the other half of your screen to open up a terminal and try these tools out. What I'm also curious about is whether, one thing that would be very nice for me if one of my colleagues can ask me questions while I present. This will adjust the speed, and also this person can be a little bit the voice of the audience. So the session will be better the more questions I get from colleague, maybe Sabri, and you via HackMD. Alrighty. What else did I forget? That's good. So I will now, let me just recapture my mouse. Here it is. I will now go into the Saga cluster and demonstrate a few things in the terminal, but I will loosely follow these tutorials. And the techniques that I will show, I don't remember them myself. So I have to look at it. I have to look for it myself every single time. I also want to show you where you can find these after the course. So whenever I look for these techniques, I go into our documentation sigma 2.no. And then there is a section under high performance computing. There is a section running jobs. And there are these two here. Choosing the right amount of memory, choosing the right number of cores. And everything I will show is in there. And I will not show everything. I will only show a subset. Whatever I miss presenting, you can read up. Now, but let's go now into the terminal. And I would really appreciate if there is somebody who asks me questions in voice and in HackMD. I will do both here. So on the other half of my screen, I have the HackMD open. Now I recommend to just watch me type. You don't have to type along. I'm now somewhere on the Saga system. The prompt will look a little bit different than on if you log into Saga. And the reason is that I changed it so that it's easier for you to read. So I put in some colors and I put the command below the path. So this is a little bit different than on your side, just so that it's easier for you to follow. Also, anything that I will type here, and let me know how the font size is. I can make it larger, smaller. Anything I will type, it will also end up here down there so that you can see what is the history of my commands. And I want to now start by a very typical scenario. I got, let's say I entered a new research group. I'm the new, I don't know, PhD student, postdoc. And now I inherited from my colleagues. There is a binary that I'm now supposed to use, and there is a run script. And very often we don't start from zero. We don't start from reading the documentation. We start from inheriting scripts from the previous generation of master students, PhDs, postdocs. So now let's look at the run script, and I will open it up with an editor called VI. Let's see what we see in the transcript. There is I put in the account and reservation for today, but now this is a run script that will actually work. So this is some binary that does something, and at the end I will maybe add calculation successfully finish. Just that I can see that this.
If I disturb you a little bit, so we have asked for 16 tasks here. So how do you? What is the rationale behind asking that number 16? Yeah,
very good question. So there are in fact, so we ask for 16 tasks. What does it mean? We anticipate that this will use 16 CPUs, 16 cores. And the rationale is that, well, I don't really know because I got the script from a colleague. And so I'm guessing that this is maybe okay. We will later verify whether this is really a good setting. In this particular example, and I will run it in a moment, it will actually work. But I'm unsure whether should I put 16 or 100 or 4. We need to find out. Also, we ask for 4 GB per core. This is maybe too much, maybe it's too little. This can be problematic. I see something else here. What is the problem with this line here? I'm asking for 4 days. And this is not a really good setting the first time I want to run this calculation. And why is this not good? Because if I ask for 4 days, it will probably be in the queue for, I don't know, half day, 1 day, 2 days. It will probably not start immediately, because it needs to find this room for this 4-day calculation. The other disadvantage is, what if I make a typo here? Instead of srun, I type sarn. What will happen is that this will sit in the queue for a day or 2, and then it will start, and then it will crash after 100 milliseconds because I made a typo. And that is really annoying. So what I like to do,
one more thing is that you have asked for 16 cores anywhere in the cluster, isn't it? So you're not asking it in one node there. So the SERM will try to find out wherever cores are available.
Yes. Here I ask for 16 tasks, 16 cores, anywhere on the cluster. They don't have to be on the same node. This is often a good starting point because I give the scheduler more flexibility to find, you know, one idle CPU here, 2 idle CPUs over there. The job will probably start sooner. Only if I know that the calculation runs better if all of them are on the same node. Only then I restrict and I ask for, I want a 1 node and I want 16 tasks per node. But I often like to start like this. But I really don't like this. So I never start with even if I know that the calculation takes 4 days, it's really not a good idea to start immediately with 4 days. Until I get a good feeling for the job, I will not start. I will start maybe with 2 minutes. And
but going back to the end tasks, you are now assuming that you have an MPI job.
Good question. How do I find out? And now I remember these tools that Ole showed us, and one of them was new to me. So I knew about LDD. Let's have a look into our binary here. LDD. This is one of the things that Ole showed. And there is a lot of stuff, but I see, well, there is something about threads and there is something about MPI. So probably this is something that can use MPI. The other thing that I didn't know, which was really cool, it was strings, my binary, which outputs a lot of things, but somewhere in there, there is some mention of MPI. So even if I cannot look into the source code and all I have is the binary, I have some feeling that this will be an MPI job, and I can run it on several tasks. But the question, is this an MPI job or is this an OpenMP job, is not an easy question. And in our documentation, we show that, well, if you have an MPI job, you can launch like this. And if you have an OpenMP jobs, you can launch like that. But finding out whether it's the one or the other or something else is not an easy task. In doubt, contact us, ask us. So here I have a starting point and I want to know, so let me maybe launch it. And let me run this thing, 4 GB per task. Well, I don't know whether this is maybe too much. Let me launch, and here still in demo mode. And you can do something like that later in the exercise. I launched the job. Let's see whether this started running. I asked the scheduler with my username. So there is a job and it's running. It's running since 8 seconds. I don't remember how long it will run, but it will run probably only, it already finished. And now I got, let me inspect that output from Slurm. I got some output. There are lots of numbers here. We will try to make sense of them. This was the command that I added. So this calculation, whatever it is, it finished successfully. But coming back to the run script, just the fact that it finished without crashing doesn't mean that these are really good settings here. And we will now discuss, why does it matter? Why does this number matter? Why does this matter? Here we already have a good feeling because Ole explained why it is so important to calibrate the number of tasks. And also we got a feeling why this matters. The shorter the runtime, the shorter our queue.
So Radovan, can you show us that output again a little bit, because that shows something Ole emphasized in the beginning. Do we have it, the log output?
Yeah, I think I will go back to the output, but I want to now go more step by step because now there is a lot, and I think I wanted to first focus on. We will first focus on the memory part, and we will have a look into the output. But I will go to a simpler example, and then we will focus on this separately. So we will have a look at it briefly. I just want to check that I didn't forget anything really important to tell. Also, I want to emphasize again something that Ole mentioned earlier, is that if I had asked for 4 days, the scheduler doesn't know that my job will finish after a couple of seconds. The scheduler assumes that my job will run for 4 days. It finished here after, I don't know, 15 seconds. So it's really important that the time is approximately what the job will take. And we need to find it out with trial and error. And then once I know, I add 10, 20% more. And here I had one job. If I go back into my folder, I have one binary, I'm running one job. But sometimes we need to run 50 jobs or 100 jobs, 200 similar jobs. And before I go and launch all these 200 similar jobs, I better calibrate. And I will now focus first on calibrating the memory. So I will go into this memory section here. And here in the text, I just don't want to forget that I want to show you why does it matter? Why is this so important that we don't ask for way too much? Because I could just let's be on the safe side and let's ask for 30 GB. Why not? Here is why not. one reason why this is really important is if you ask for too much, you might get charged too much, because every CPU has approximately 2 GB. If I ask for 8 GB per task, it will have to allocate 4 CPUs for each task. So I will block more CPUs. Other people will not be able to use them. I might get charged more. So if you ask for way too much, you might be surprised and see that your account suddenly has a lot fewer compute hours. If I ask for excessively too much memory, I may also queue longer, because it has to wait until it finds enough cores available to accommodate my job. So I will queue much longer. It may limit the possibility for me to parallelize my job. And to explain that, maybe let me zoom back and look at, in our documentation, let's look at the Saga cluster here on the hardware specifications. There are a certain number of nodes, certain number of cores, and each of them has a certain amount of memory. And if I ask for way too much, there may not be enough cores available for me to parallelize to run them at the same time. So this can be really limiting for me. Here we have it. We have how much memory is there on each node, how much memory is there on each core. If I ask for too much, I can't run too many of these things at the same time. All right. Now on these, I think I'm on the wrong page here. I need to go back to the, where was it? Running jobs, right amount of memory. So, I just want to zoom in. So now in the next few minutes, I want to show you some of these techniques that I can use to find out how much memory does a job consume. And there are a couple of techniques. I think I want to show you maybe 2 or 3 out of these. First, let me go into an example job. And I'm here following the documentation, but I invite you to watch what I do. So I will go into an example. I have here a binary where I don't know how much memory it consumes. And one way I will first comment this out, and I will run it as it is. And I want to now look at this output that we get from Slurm. Here I'm generous, I'm asking for 3.5 GB because I don't know. So one technique is to ask for too much and then decrease until it crashes and complains. But I want to show you that there is a better way. But let me first run it as it is. As batch, I submit it. We will get an output from Slurm, and then we will inspect the output together. This job takes 35 seconds. This gives me some time to have a look at HackMD.
So Radovan, can I disturb you as you're all showing the file that I... So you see that you have allocated the C2-22 machine there. So in the previous log file as well, you allocated 1 node, although you asked for 16 cores and you didn't mention how many nodes to allocate. That job was allocated exactly 1 node. So this shows us some limitations of the things that we are showing. For example, if you bring a code from somewhere else, and if you just run it, and if the core count is different in different clusters, for example, on Saga, 32 cores means you will get 1 node, like you could get 1 node, but on From it might be 40. So you can't without blindly, you can't just compare results from one place to another. So if you're borrowing code, you should also know some idea of how much memory that you showed each node has, how much cores you should have. Like you should also have some background of the cluster.
Good point. And something that is many people get wrong, which also confused me, is that it mightn't be so clear when I ask for a certain amount of memory. Is this for in the entire job, or is it per CPU, per core? And here I ask for 3.5 gigabyte per core, and I only ask for one task, one core. And I'm sorry for using these CPU, core, and task. In this case, they mean the same thing almost, but for historical reasons, they are these three different names flying around. Let me see whether my job finished. It has finished. There is now this Slurm output. And let me inspect that Slurm output, whether we can see something in there. And it is a little bit hard to read because of my font size, it's wrapping around. I can make it fit into the screen, but then the font gets tiny. But one place where I can look at for the memory is this number here. Average residence size. I don't know what the last S means. And the max one. This is given in kilobyte. So this mystery binary is using 3.2 gigabyte. And so I was lucky because I have asked for 3.5. So it uses 3.2, it fits. If I had asked for 2.5, it would have stopped with out of memory. So this is one way to go into the Slurm output. I don't think this is the, I don't know, there are lots of numbers. I will show you two other methods that I like to use, and more methods are mentioned on the documentation. So one thing that you can do is you can prepend your binary with this command here, and it will give me more information. I will run it again. In the meantime, while it's running, I can also mention that it's good to know that Slurm measures the memory every 30 seconds. And this is also the reason why I let my job, so this binary runs for 35 seconds, because I wanted to fit into the frame rate, into the rate of measuring. If your job is shorter than 30 seconds, Slurm may report that it didn't use any memory at all. Also, since it measures every 30 seconds, if I allocate a lot of memory between these measurements, Slurm may not even notice this. That's why also I like this other command. And the other command, now I look into the new Slurm output. In this Slurm output, there is output from Slurm that we recognized from before with some numbers, and there is this number here, but now I also got some output from this time command. And the interesting one is this one. So I personally like this because it's for me easier to read. I think it is also more robust with respect to how often it measures itself, how often it measures this. So this will really measure the high watermark of the job. And I want to show you one more tool that I like to use. And that is if you know your job number and if the job is already finished, you can use this wonderful tool called SF, something like Slurm efficiency. I don't know exactly what it stands for, but I can ask with my job number and it will tell me interesting information. There is information about CPUs. This will be useful in a moment when I talk about CPUs. But it also tells me how much memory did it utilize. It utilized, here it tells me 3.06 gigabyte. And why this is now different? Well, it can also, this can be, did we multiply by 1000 or 1024? So there are these different conversion factors between gigabyte, megabyte, kilobyte. but I really like to use this tool to get an idea of the memory consumption. It also tells me that I have used 90% of the memory that I have requested in my job. I think this is pretty good. If I went overboard, it would stop my job. All right, let me see, any questions? Not too many questions on HackMD. Please keep the questions coming. Any more questions about memory before I move on to cores?
So Radovan, when you mentioned in your previous job that you had 16 tasks and cores per mem per CPU some value. Mm-hmm. So you had to, so one thing I learned was, like, let's say if you say 3 gigabytes per CPU, like the job will not crash if one of your threads use more than that. So you get a pool of the amount of memory. So here, the previous, now here it is only one task. So it's exactly 3.5 gigabytes. So
okay, so what if I had more? If I had here?
Yeah, 2. Then you have to make sure that 16 means 3,500 times 16 should be available in the node. And also, just because one of the cores use more than 3.5, the job will not crash. But all the threads together, if it exceeds 16 times 3.5 gigabytes, then the job will crash.
Yeah, so it can, depending on the type of calculation, it can be advantageous to specify per CPU or per entire job. And there is a way to do that. Also, how many cores are there on Saga? 40? I think 40, huh? On one node. I could find out asking documentation, but I think it's 40.
So it is 40 cores on Saga, and in general nodes, it's 32.
Yes. So let's say now we are on Saga, and I think I remember that on Saga, each core has 2 gigabytes. But what if I do this? Can I do that? I ask for 40 tasks and 3.5 gigabytes each. So what will happen then is that the scheduler will allocate for me more than one node. It will not fit on one node. So if I would launch this and see how many nodes I get, I will get at least 2 nodes, because it will spread the calculation over more than one node. And this, now we also understand that if I ask for way too much memory, I can block many CPUs that will be idle. All they will do is they will donate memory, and then you may get charged for it. So there are also high mem nodes. If you need a lot of memory, there are high mem nodes on Saga and on the other clusters probably also. And these are the more appropriate nodes if you have a high memory consumption job. Good. So now we discussed time briefly. We discussed memory. There are more techniques to find it out, but I will not go through all of them. I would like now to switch over to discussing the number of cores for 12-13 minutes. We will then take a break, and after the break we can try this out also on our own. So let me switch to the different page, which is also linked from the HackMD, and which discusses choosing the, well, no, I'm still on the wrong one. I want to go now to the number of cores. And the motivation, so there is no tool that will tell me how many cores I need. You will need to calibrate it. You will need to run a series of calculations, and you will need to compare them. This is also, Ole has emphasized that a couple of times. There is really no other way. And again, why does it matter? Because it's good for you and it's good for others. It's good for you to have a reasonable number to calibrate this number, because you will get more calculations through the machine in the same time. It's also really good for others and for the taxpayer if we don't block resources for others that others could use to do other interesting science. There are different techniques. I want to show you two techniques out of this page. And for this, you can still please, I will leave this here. Please still watch me demonstrate. You will get later the chance to practice. And thanks for the questions coming in. I will watch and discuss those of general interest. I will now go to a different folder, but I'm using the same example as in the documentation. This example code, I have compiled it into this binary, and now I have a run script. And this run script will run this job. This is a job that doesn't take a lot of memory, but now again, I'm running it on 8 cores. I don't know whether this is a good setting. And sometimes we have seen run scripts where users ask for 16, and there is really no good reason for it. The only reason was that they got the run script from their colleague, and long time ago, there was a cluster in Tromsø that had 16 CPUs per node. And many years later, a couple of generations later, this is still in the run script. And it may be that this is not a good setting at all. So really good to calibrate. And I want to now show you how I calibrate these things. And I will also show you some of the tools that can help me finding out how efficiently this run. So let me ask for 3 minutes. This here I'm asking 8 tasks. I don't care where they are. They can be on the same node or on different nodes. I will rename the output to 008 so that I can then compare output with other runs. And this calibration that I will do now, so what I will do is I will run it on 8, on 16, on 4, on, I don't know, 64, and I will compare the timing, and I will compare efficiency measurements. And this is important to do before, again, I run 200 similar calculations. And even if the website says, even if I go to the website and on the website it says, this code is really parallel and it's very efficient, it's still important that I verify this, because even if this is a code that is well parallelized, it can depend on what functionality do I use. It's really good to verify this first time you run. Okay, so what do we do? 3 minutes, 8 tasks. I load some modules, and this is an MPI parallelized binary, but the fact that this is MPI doesn't matter much at this moment. But what we will see, this is an executable where it does some computation and it does some communication. And as I will be adding more and more tasks, so I will do 8 and 16, 32, 64, 128, we will see that at some point, it will not make sense to add more tasks to it, because at some point, it will spend most of its time communicating. This is a bit like, I don't know if you have worked on a research project with lots of people, or if you work on a manuscript with lots of people. At some point, if the team or the project gets so big that there are so many people involved, you maybe spend all your time in meetings and emails, and you don't have so much time for actual work. And it's similar to a calculation where there is a lot of communication happening. Let's try it out.
So Radovan, before you go out of this, not more often, but lot of calculations, they involve some data sets. So now your example, it's sort of easy to understand what's going on. So if there's a data file and you have some big data file and we want to see how much it will consume, is there any suggestions that you would like to make?
So you mean
like
how much?
If there's input in addition to your program, how would you go about what you're doing now? What would you do differently?
I would do nothing differently. I would also run a series of calculations on different amounts of processors and compare the timings. But then I would also look into some of the tools that I will mention that will give me a little bit more detail, because they will also tell me, out of this computing time, out of these 3 minutes, let's say, how much time did I spend computing? How much time did I spend waiting for memory? How much time did I spend communicating? And how much time did I spend waiting for the disk? So I will get a bit more information, but the approach is the same. Run it until you get a feeling for what is a good setting. And what I also like to do is I like to start small. I start with a small example and then I grow it until I get a feeling for the system. So instead of starting with 4 days and 2,000 tasks, because I will just wait forever, I rather start small. I start with minutes and I start on 2-4 tasks, and then I grow it until it looks good. And then I run all my calculations. All right, so now I will say maybe not much more than 10 minutes before the next break. Let me run this thing. I will launch it. And the way I do it is, one simple way is I will copy the run script into a couple of other run scripts for 16, 32, 64. You can see where this is going. Of course, they are still wrong because I need to adapt them. Let me fix those. So here, what was it? This is 4. I need to ask for 4 tasks. So it's a little bit annoying work, but this is 8. This is correct.
So Radovan, you could also specify this as arguments for the batch, for example.
Oh yeah, that would have been better. So instead of creating all these files, what I should have done really, I should have all these arguments to sbatch. You can also give them outside as arguments on the command, and then I wouldn't have to create all these files. So this would have been more clever. But I'm already on this pedestrian track here. I will just finish. 32, 64. This gives also people time to ask more questions here.
Yeah, and I also see that you are renaming your output file, so it is easier to find out which output file is from 128 tasks, for example. So you specify that explicitly.
Yes, so that it will be easier for me to compare, because then I don't have to remember which job number was which core setting. I will get all these output files. And now let me launch them all on one go. So I will now do some advanced shell scripting for file in run do as batch file done. So now I made a loop and I launched them all in one go. Oops, there was an error. Okay, in some, maybe I asked for too many. Maybe I asked for more than it was in the reservation. That's not a problem. And now I patiently wait. Finished a little bit quickly. And what I would do is go in. One of them is, so there is somewhere in the slum output is my binary. Sorry that this is wrapping around. And now what I would compare is the runtime. So now it spent 9 seconds on, where am I, at 8 cores. What will I see if I do grep my binary? So now I extract from all these output files. From all the output files, I extract only the line with my binary. And now let's see whether this makes sense here. So this is maybe not such a great example, because as I'm adding more and more cores to it, and I have 2 runs with 8 cores. The time goes down. So from going from 4 to 8, time goes down. Going from 8 to 16, time goes down. Going from 16 to 32, time goes up. Going from 32 to 64, time goes up.
So Radovan, you mentioned something about sampling time, 30 seconds. Does it matter in this case because all the values are below 30 seconds?
In this case, it doesn't matter because the sampling time was to measure the memory. Here, I'm more interested in the runtime. It's still another good example because the runtime is too short. It takes some time to start up. It takes some time to allocate these different tasks, distribute the job, collect it at the end. So in real life, what I would aim for when you do this comparison, try to compare a job where it takes not just very few seconds, but ideally where it takes minutes. I like to take something that maybe on 1 core takes 1 hour or 2 hours, and then I compare. So ideally, I would like to have something here that takes maybe a minute or 2. And I think today, if things were just to run faster, then, so of course I have prepared this example. So when I ran this, a few days ago, this is the result that I got. It's still a little bit too short, but what can we take from this? What I would take from this here is that this really runs well on 4 cores or 8 cores. Doesn't make sense to add more to it. It will just cost more. But I would probably try to increase the system size to get something that runs a few minutes here and run this again. And I will probably get a similar answer. So here it doesn't make any sense to go beyond 16 cores. It's a waste of resources.
So here I would like to make the previous point, Radovan, about how many nodes were allocated should also be maybe considered. Because yes, you grabbed your MPI, short MPI, but whether I could actually did the MPI, we didn't do a top command or anything to check it. So number of nodes allocated might also be interesting in this. Maybe the 16 cores was in different nodes.
Yes, this is a very good point. And it's a good point for several reasons. If these tasks are on different nodes, they are further away from each other in terms of network. So it can make a difference. Also, one thing I would verify, and this is what Sabri mentioned, is that when I run it for the first time, and I would like to have something that runs a little bit longer, is to submit it, find out on which compute node it runs, and then SSH into the compute node and have a look whether the number of tasks running is what you expected. Sometimes you think that I spread my tasks among 4 nodes, but then you log into them and then you see that all of them are stomping on each other on the first node and all the other nodes are idle. So this is also something good to verify.
And also the ceph command you showed before, it will also show the efficiency of these jobs.
Brilliant, brilliant. So this is also what I wanted to show. Now let's try the ceph command is a super tool, but you should only use it on finished jobs, not on running job. But all of these are now finished. So I can now ask, so fortunately I know the job numbers. So what was the efficiency of that job here? This was something that ran on 8 cores on 1 node. Here we are not so much interested in memory. And you can see that the memory efficiency, well, I'm not sure this is right, but this is because the job was very short. But the CPU efficiency here, the CPU was busy 50-60% of the time. Let's see what happens if I ask the 64. What's happening there? Yeah. So here it was running on 32 cores. They were distributed over 2 nodes. CPU efficiency, similar. I think the job was too short to see a meaningful difference in terms of CPU efficiency. As I would go to more and more cores, I would see this dropping down. I think I want to show you one more example that I prepared, which may maybe demonstrate this further.
This efficiency is affected by 2 nodes as well. There's MPI communication going on in this.
That's true. So I would like to take a break in 5 minutes, so 5 more minutes of demo time. I will show you one more example that, ideally I would like to show you 2 examples. There is, on the same page, there is one example where I can, now I would like to know a little bit more. I can find out it runs well on 8 cores or 16 cores, but what if I want to know more about why it scales or why it doesn't scale? And here I have an example. Memory bandwidth. And what is inside this one script? Now I will use a tool that can give me a little bit more information. This tool is mentioned on the website. It's this perf report. So instead of running my binary, and here I will run it on one task, I want to know, does it compute? Does it spend waiting for memory? Does it spend waiting for disk? So I'll run it through this tool. And what you will get, I think it will also run 30 seconds or so. We will get a report from this tool and a little bit more information on efficiency. Just catching up with HackMD. Yeah, there is a question about Ceph and GPU. Can we give information about GPU usage? And I don't know. So I don't know enough about GPUs on our cluster. Maybe we can come back to that tomorrow, but I don't know the answer. If one of my colleagues knows, I would be happy to learn. This is still running. I think I made it run approximately 1 minute. And it will finish soon. So that's what I do on the cluster all the time. SQ, SQ, SQ. Does it start? Does it finish? It finished. I got now some output from Slurm and I could peek into it. But I got something else. I got these report files from this perf report. One is an HTML, which I could download to my computer, open in a browser, and it gives me like nice graphics. But instead I can also open the text file, which has the same information, but in text format. So let me have a look. Text. It tells me what did I run. I ran something on 1 core, gives me information about the compute node, and here we go. This gives me information on what is the amount that I spent in computing, in communicating, and in disk. There was no communication, there was no disk access, but I spent time computing. But now you can break down this compute time into different components. So 90% of the time, my job spent waiting for memory. So this is a memory-bound job. And does it make sense now to buy a faster CPU? I can buy a faster CPU, but it will not run my job faster. So this particular job is limited by memory access. If I wanted this to run faster, I would have to go in and look at the algorithm and try to change the data structures. So almost no time in this job is actually spent computing on the CPU. So with this tool, you can get information about communication time spent in communication, time spent in disk. In this case, there was nothing spent. Good. I wanted to show one more thing, but I'm not sure I have time. I think what we should do is to take a 10-minute break. And after the break, I will maybe show one more thing, but then I will explain to you an exercise. And in this exercise, you can try these things. You will be able to try these tools yourself. So I will give you 2 mystery binaries. And in one, you can try to find out how much memory does it consume. And the other one, you can try to find out what is a good setting for how many cores it should run on. But I will explain after the break. So let's take a break until 51 past 11. Sorry, sorry for that. I would first like to explain what is expected. And I would also like to give an outlook of something that I will not discuss, but I want to point you where it is. So there are some of these tools to find out efficiency, but really one of the best things is to run a series of calculations. It's also the simplest approach. On the bottom of this documentation, and I will not go into this, but I wanted you to know that this is there. Very often we run code that we didn't write. It's code written by somebody else. So how do we know whether this is an MPI calculation or an OpenMP calculation or independently parallel? It can be very difficult to say. But here are some hints on something you can try in addition to the LDD and in addition to the strings command. And in particular for those of you using Python or MATLAB, there can be situations where you can also make use of having access to multiple cores, and it might not be immediately evident. If your Python or R code is using another library which may be parallelized. And down here, there is an example for those of you using Python, which you can try later or during the exercise, where you can try to run this Python example with these lines active or with these lines deactivated, and you will see a difference. So also for languages that are not traditionally made for parallel computing, you can make sometimes use of having access to several cores, and it can be useful to study this. Or ask your colleagues, or ask support if you are unsure. But now let's go back to the HackMD, and I want to explain to you the exercise. And I think we may not have 20 minutes, but we will have 15 minutes at least. And so on Saga or on, oops, here we go. On Saga, you find this folder. This is also, if you have done the exercise earlier today, this is the same folder. In that folder, you find 2 directories. One is called how much memory, the other one is called how many cores. Let me show you that. You can maybe start with one of the 2, the one that you find more interesting. So if I go in there, there is Day1. How many cores, how much memory. Inside these, there are these mystery binaries, binary I, binary B. There is a README file, there is a run script. You can run it as it is. It will run and it will complete. It will not crash, but it doesn't have the optimal settings. So your goal is to find out, using one of these tools that I mentioned, how much memory is consumed, what is a good setting of cores. Also, we should always be careful running some binaries that we got from a stranger on the street. But here, it's the same binaries that I have built and using the same source code as on the website, but with different parameters. So it's not so that there is a bit of a mystery for you to find out what the values are. And you can start with one of the 2. If you have time, try both. You can also try the tools on one of your own code or own run script. Super. So please use the breakout rooms, 15 minutes. It will be until 12:10. Then we will come back.
Yeah, everyone should be here now. Rooms are closed.
Super, welcome back. I hope the time was not too short, probably was too short, but please let me summarize the take-home message from my session. What I can recommend you to take home from this session is that if a job is not crashing, it doesn't mean that it's running well. And it's good to put a study, even when a job finishes, whether to calibrate memory a number of cores. We have seen a couple of tools, not all of them, there is more on the website, but the one to remember is Ceph. Really nice to run it on any of your finished jobs. It will give you information about CPU efficiency and memory use. I think it is a good practice to grow a calculation from small to realistic, from short to realistic, and also to do a series of runs on different configurations of cores, nodes, maybe GPUs. This takes some time. It will also eat some of your compute time, but I think it is not a waste. Also, this is not something that we need to do every single time. When do I need to do this study? I recommend to do this study when you are maybe moving to a new machine. Maybe you know the calculation really well on From, but what if you move to Saga? It's really good to study how it performs there. Moving to a new machine or moving to a new code. And even if this is a code that you know really well, moving to a different system size or a different functionality, it can have a completely different memory profile or a parallelization profile. So it's good to put a study on that. And I believe that this will really save you a lot of time. It will save us resources. And really what we are all after is maximizing the number of papers and science produced per year on the Norwegian clusters. So this is what it's all about. And I think I will now go to give back microphone and screen to Dania for discussion session.
Yeah, please, before that, could you share this HackMD? It's already there since, so I'm asking the feedback for the day one. One thing you thought was good, and one thing you think that we should improve, and we will take consider of this for tomorrow's session. So,